We have maybe in-space manufacturing possibilities, bringing 3D printers into space, which can build huge solar sails, and we just use photon pressure. So the sun does not only provide us, light, but it also has a momentum, and that's fantastic. We can sail around the solar system, and well, Breakthrough Starshot wants to go interstellar with that.
Hello, space enthusiast. You're now listening to Space Forward Podcast. I'm Hussein Bukhari, your host. With me are Matthias Frenzel and Benjamin Shapiro. In this show, we ask space scientists and enthusiasts what is needed that humankind becomes a multiplanetary species within our lifetime. While we're asking the hard questions, we attempt to break down complex space ideas, the first principles, and deconstruct them into digestible chunks. Today, we'll take you on a deep dive into the physics of space travel. Are we merely grappling with a challenging engineering problem, or will new breakthroughs and entirely new physics be required in order to utilize space to its fullest potential? We will discuss this question with our guest, Professor Martin Tajmar, renowned Austrian physicist, professor, and chair of space systems at Technical University of Dresden, and hurray, a fellow International Space University alumnus, a member of the family. Martin has worked at NASA, ESA in South Korea, and the Austrian Institute of Technology, performing research on electrical and miniaturized propulsion and on breakthrough propulsion physics. Professor Tajmar is the author of the book Advanced Space Propulsion Systems and has received critical acclaim from the scientific community for his research on electric propulsion. Hey, Martin, great to have you on the podcast. Martin, one of the things that I'm hoping that we can dive into today, and the idea here for this episode is getting to the depth and the concept of physics of space travel. You're a physicist, your master's and your PhD theses both were on electrical space propulsion. What brought you into physics? Can you recall a particular time or moment that represented a turning point? And it was like, I'm going into space and I want to research electrical propulsion for the rest of my life and become a physicist.
Well, that's a fairly easy question because if you asked me as a 5-year-old what I would like to become, my answer was I would like to become a physicist. People asked me if I know how to spell this actually, and so it was very clear from the beginning that physics, that's what it's going to be. And when I watched Star Trek on television, I knew that someone has to build the warp drive, so that's going to be me. So physics and space and this combination, that was very, very attractive for me. I began this really very, very early on, and this was a big advantage for me that I had this clear path in front of me, so I knew exactly what to do. What I'm doing now at university is the same thing that I did as a child in my children's room, in my laboratory. Just I'm now doing this in order of, many orders of magnitude better, but I'm doing the same kind of experiments that I was doing as a child. So I'm very, very fortunate, very lucky. And I always knew that it's going to be that.
This kind of poses a very interesting question, and I've been always curious because I've listened to a few interviews that you've given. What kind of gave you the inspiration and the motivation to entice you into the research that you're doing right now in space propulsion, and what you're calling breakthrough physics and breakthrough research and breakthrough propulsion. What has led you to that?
Okay.
Give our audience a little bit of a background there.
Sure. Well, I kind of figured out that the most important thing on your spacecraft is propulsion, right? So if you look at Star Trek, I mean, it's great to beam some people, to the surface and back, but I could do this also with a shuttle. It would be nice to have, a food processor, whatever, but I could also bring some frozen food with me on the trip or so. But I cannot trade in, the warp drive. I need propulsion to do the really fun part. So that's the number one item. And so space propulsion and I really have to dig deep into space propulsion. And yeah, when I learned about the basics in propulsion and what you could do with it, and I realized pretty quickly that whatever we do, the best technology that's around can just bring me to the edge of our solar system. And well, that's not very far because, of course, I would like to explore other worlds. You know, maybe find other people somewhere. Yeah, and so you need to get to the next stars somehow. So that's the biggest problem to solve. And and it's really the biggest problem to solve because there is no path that you can follow that will be successful in the end. So it's one of the biggest mysteries and one of the biggest puzzles to solve. And I thought that that's great because you have to take on a very, very challenging problem if you want to achieve something. Maybe you don't achieve that, but along your way, you must be very innovative and you get so many other things that you maybe didn't think about. So you need something very challenging to achieve something big, no matter if you achieve this goal or not. So I chose that path.
Well, it's very admirable, especially I'm sure to our audience that you're taking this path of trying to figure out and trying to go to the next, trying to create the next revolution in this spectrum. But one of the key things that really got me was you're also a international space university student, and you went there. What we're hoping to learn from you is not only that you were a student but you also lectured. Are you still a faculty there? How was your experience as a student, and becoming part of the space mafia, as people like to call it now?
All right. Well, I can tell you that when I was at ISU, this was my best time as a student. Yes, so this was the best time, and not only that, with the people interacting and all these things around ISU, but what I particularly enjoyed was that every day I learned something else, from space. One day it could be space law. The next day, they bring in the president from the Japanese space agency. Yeah, I'm exposed to something completely different. Then the next day, the shuttle launch director, yeah, from Cape Canaveral. It was so fascinating to see all these different aspects of space and to talk to key people in that area and to build up your network. Yeah, that was fantastic. So yeah.
It was a good setting stone for you, and guiding yourself into the space trajectory that you are in now. And coming back to that spectrum of space trajectory that you're leading on now, or that you're moving forward on now. One of the things that we're hoping to do on this episode with you is deconstruct the big ideas around to first principles. To get our audience to actually understand what does it mean when you think about physics and when you think about space travel. What would you say are the basic fundamental concept in physics relevant to space propulsion?
Okay. The basic principle is actio reactio. So that means I have to, I have to create some momentum and I get a back reaction. So that's the core principle on which all known propulsion systems work. Which means I need to have propellant and or energy to achieve propulsion. And there are some severe limits to that. So if I have to bring my propellant with me on this journey, then I end up pretty fast. I end up in a certain limit that if I want to achieve, let's say I want to achieve a certain end velocity with my spacecraft, I have to use all my propellant. This propellant must be very energetic, so it has to eject at a very high velocity in order to achieve my, let's say, end velocity. And if I want to go a little bit further than that, then I do not have to just bring a little bit more propellant with me, but I have to bring much more propellant with me, because for this little add-on, I have to bring all this additional propellant in addition. I have to move it to my original velocity, and then I can do the add-on. So I always have to add a huge chunk of propellant initially to do then the little add-on at the end. So this is called the Tsiolkovsky equation. This is the basic equation in space propulsion. And yeah, that means with the options that we have, so with the efficiencies, with the energies that we have in propulsion available right now, and with the amount of propellant that we're used to carry with us. So the basic limits that we have is then basically, yeah, the edge of our solar system. And that already involves, very fancy propulsion systems like nuclear propulsion. So nuclear propulsion, so if you just compare, so if we go through some of the options, right? So you have chemical propulsion. So that's the workhorse of present day propulsion. Well, you take, for example, hydrogen and oxygen. This is a very, very energetic combination. You would like to arrive at an end product that is a gas. Yeah? So that limits you in some possibilities. And you would like to have something that is probably also not, which is green and not toxic and so on. So actually that means that hydrogen oxygen is the best choice. Yeah? You can maybe replace hydrogen, let's say, with methane or so, what SpaceX is doing, which is fairly similar. And it has the advantage that methane has a higher density than if I would just take hydrogen. Yeah? So hydrogen is the lightest gas around. So I get some improvements there. But that already, if you take these best propellant options, it doesn't even bring you into orbit. You have to actually, if you want to get into orbit, you have to do this in at least 2 stages. So you cut your rocket, and well, SpaceX, fortunately, they can reuse this first stage now, and it's coming back. It's being reduced, but this whole huge tank and everything that you carry with you, this is just dead weight that you don't use anymore. So you have to cut your spacecraft in at least 2 pieces. And let's say if you would cut your spacecraft or your rocket into an infinite number of pieces, that just would give you a factor of 2 in your improvement. Yeah. So if you cut your rocket in half, this brings you about a factor of 1.4. And that is enough to bring you just into orbit. If you slice it in a million pieces, you get a factor of 2, which is, yeah, it's a limit. Yeah. And so chemical propulsion, yeah. So the idea is now you go into space, and then, well, you have to launch many refueling missions to inject your rocket in space now with more propellant, and then you can go maybe off to Mars. You can maybe go off to Jupiter. This takes a couple of months. That's possible. It's it's expensive, and it consumes a lot of propellant.
Yeah, yeah. One of the things that you brought up a really good point, and I think our listeners would want to know. You mentioned the division of rockets in multi stages and increasing by a factor of 2. And this kind of leads into my next question. What is a factor of 2, and what are some of the key metrics other than the factor or other than the division of multi stages that current space propulsion or traditional space propulsion can use to optimize its capacity and its improvements?
Yep. So basically, this this very basic rocket equation is the Tsiolkovsky equation. Doesn't give you well many options to work on your improvement stuff. So there is this mass ratio that you can play with, and there's a so-called specific impulse. So this is this energy in your propellant. It's the propellant utilization efficiency. So it's basically the speed that your propellant has when it exits your propulsion system. And yeah, if you have that's why I said if you have chemical propulsion, you have a certain energy density. Hydrogen oxygen is already the best. If you don't go toxic, you can say, well, I don't care about going toxic or not. So I'm launching, let's say, in the middle of the ocean. There's no regulation. I don't care. Yeah? So maybe there's a Greenpeace ship coming or whatever. But if I launch quickly, I can get off. And you can replace oxygen with fluorine, for example. Yeah. So then you get a nice acid coming out on the back of your propulsion system. That gives you some little improvement factor here. But of course, this is not very nice because your launch town, whatever, will be destroyed by this acid. Yeah. So that's not so good. So there are a couple of, let's say, propellant options, some exotic propellant options that people are thinking of. For example, something like metallic hydrogen or so, something which is stored, a very cold state under enormous pressures and whatever. Maybe in the future, you can think about something like this. But very naturally, the next big step is not to use chemical explosives. We all know there's some much better explosive around, and that's a nuclear option. So if you go, doesn't matter if you go nuclear fission or if you go nuclear fusion, then your energy density goes up by something like 8 orders of magnitude. So this is not a factor of two. Forget this. You just go, many orders of magnitude above. And this is technology that is around since the 1960s. It's just a political thing. So if you have a requirement to use this kind of option, then governments can take the card and just implement it. So that has been done. You can, with nuclear propulsion, you could in principle, you can launch with a spacecraft from the Earth, fly into space like an airplane, come back without cutting your rocket into pieces. And you could go, on a manned mission to Mars in 1-2 months, and in half a year you can go manned to Jupiter. So that's a really nice option. And I always compare, in the old days, let's say 200 years ago, people were going with a horse carriage, right? So when they were going, let's say, from Germany to Italy and back, it took them also something like 2 months or so, 2-3 months. That's a time that with nuclear propulsion you could go to Mars. This is a good option, right? It's like in the old times.
But why hasn't nuclear propulsion been an option since the 60s as is it's becoming more and more prevalent now?
Well, I'm very sure that in at least 10 years or so, this nuclear propulsion option will be available. Yeah, because the Chinese are going to do it for sure. And if they are doing it, the US will do it. Yeah. And Russia has it, also in their pockets. They're just waiting, to release this kind of technology. Of course, everything that deals with nuclear, that is. You have to convince the public and whatever to do that. Huh? And of course, you know, the plan also was, for example, to use this only when you're already in space. Yeah, so you launch this and you activate it when you're in space. If you don't activate the reactor before and the rocket explodes, so what? You would not even measure any kind of increased radioactivity. Yeah? Um, so that's for example one option to do so. Yeah, again, this technology is around since decades, and it just waits to be used.
It seems like it seems like it's been a very steady case of keeping the technology development slow but steady and waiting for the right time for it to come. But one of the key things that we're trying to figure out through this episode and with you are the factors that space propulsion would hopefully be overcoming. The limiting elements. And it specifically for literature, it's defined as gravity, inertia, that come in that domain of limiting elements. That how would you put that? How would you put that? Are these the only two main elements that are limiting us to improve and enhance on space propulsion physics itself?
Well, again, as I said, there is no method that we know of that works for sure. Yeah? I can give a couple of ideas how you would hypothetically do it,
Absolutely.
and we can go through that.
Yeah,
Yeah,
absolutely.
so
Hypothetical is where
okay,
everything starts, right?
okay, great. So the magic thing, okay, if you discover this, is -1 kilogram. If you discover -1 kilogram, we are done. It's very easy, yeah. So you can just put this forth. You can go and find -1 kilogram, and we're done. We can go to the stars. Why is that so? So the key thing here is mass, yeah, and especially, let's say, inertial mass, yeah? Because inertial mass, it's linked to the force, to everything mechanical that we do. And if we have a rocket flying, whatever, that's all mechanics. Okay, so it all relies on, let's say, good old Newton's mechanics. Force is mass, inertial mass times acceleration. Yeah? And so if you want to change this somehow, you have to work on the mass, on the inertial mass. Yeah. And just two examples of how this could work. Option one, you maybe achieve to change your inertial mass by a little bit. Yeah, very small amount. Um, yeah, for example, let's just explore this a little bit. E is mc square, everyone knows. Energy is mass times speed of light to the square. So which means, let's say I have a capacitor and I charge this capacitor, then this capacitor will increase in its mass, because I increase the energy and whatever. Yeah? By the way, in this example, the power supply must be external. It's not going to be in the spacecraft, because then it will just shift energy from one side to the other side. But in just our example, I charge up a capacitor from the outside, and so it increases in mass. And when I discharge it, again, going to the outside, then on my spacecraft, then the mass would decrease. So if I find a method to somehow do this exchange with my environment, to, a little bit of mass goes to the outside, and then when I need it again, I will bring it back, that would be something, because then I could do the following. Let's say my mass is a little bit bigger, and I push it, and then I wait until the mass is a little bit lighter again, and then I pull it again. And the push and pull when the mass is high and low, and that means I can I could move in space-time with that without expelling propellant, yeah, by giving something to the environment and taking it back. Yeah, so that's for example method number one. The really cool method is method number two. In method number two, I say that, hey, let's say I achieve to go even negative in mass. Yeah? So now I'm not changing mass a little bit, I'm going negative. Yeah? If I do that, then if I have positive and negative mass next to each other, negative mass is actually something totally magic. Yeah? So it's a magic trick, okay? If you have normal mass on your table and you push it, this mass is going to accelerate in the same direction as I push it. F is m times a. Now I do the magic trick. That stuff becomes negative, which means I try to push it and it's actually coming to me. Okay? It's totally weird. And you can say, hey, has this ever been observed in the lab? The good news is yes, it has. So our technology becomes better and better, and we can actually create our own little universe in our laboratories. And you can actually bring matter into the state of that it behaves like if it would have negative inertia. Yeah? There is some great papers out there. One of the most famous physicists in Austria is Professor Zeilinger. Yeah, so the head of the Academy of Sciences, very well known professor. And in the 1990s, he did lots of experiments with neutrons, actually. And nowadays he's very well known for quantum teleportation, yeah, so doing lots of stuff with photons. In the early days, he was actually doing lots of things with neutrons. And for example, he also investigated if F is m times a, so like Newton said, also for if you would have negative mass, does Newton's law still hold? Because this magic trick that I told you, I push on something, a negative mass, it comes to me. Who knows if this is true for Newton's law? Yeah, Newton wasn't aware of this maybe he thought, maybe it's the absolute value of mass times acceleration, that's force. Yeah, he didn't write it down because there's no negative mass. So let's try to investigate, does such a case exist? And well, what he showed was that if you have a neutron beam, and this neutron beam actually at the right angle with the right energies and whatever goes inside a crystal, then this neutron beam splits. One beam behaves as if it would have positive effective mass, and the other one behaves as if it would negative effective mass. And then they looked at the following, this neutron beam, this split, and was going in the same direction, and now gravity is acting on both, right? So gravity pulls down the positive neutrons and they fall down. And gravity pulls on the negative mass neutrons, and actually they go up. So you see that this neutron beam is actually, splitting because both are being pulled, but for the negative mass neutrons, they're flying upwards. So there's a great paper out there from Professor Zeilinger. The title is something like, neutrons that fly upwards in a gravitational field. I would give him the Nobel Prize for that.
And so would I if I was part of that team. But one of the key things that or one of the things that I'm starting to understand, that a lot of these fundamentals that have evolved into conceptuals, that have evolved into broader ideas and formulation of different segment and segmented into multiple different approaches. It is a challenge that each one of those are facing today to bring it out and become a prominent becoming a prominent standalone against what we already have, which is chemical propulsion. We know chemical propulsion works because we have done it for thousands of years, and we're trying to still improve. It seems like we're still trying to improve a lot of the factors that involve chemical propulsion. And this has evolved that original Tusalsky equation into a much harder problem. But, in order for us to, as a human species and as people who are continuously solving challenges, to get to the Earth orbit and to get there faster, but not just that, but to get to interstellar, what is the hardest problem that you think that we have to solve in this realm?
Well, again, it's two different things. So to get into orbit, it's just time and money. So SpaceX is solving this for us. That's great. So this is actually, something that maybe an opportunity appears, once in a century or whatever, that the richest man in the world decides to put his money on solving space travel. That's fantastic. Yeah, so it's just time and money, and with some good engineering. So the way how they do it, they improve the rocket engines. They have right now a combustion efficiency of something like 99%. Well, there's room for improvement, but the gain is going to be really small. Okay, so I think chemical propulsion is already, it's there. Yeah. So they're trying now to improve the thrust over weight ratio. So they're trying to make it more lightweight. They increase the pressure, so they have more thrust and whatever. Yeah. But from the energy that they put in to the energy that's coming out, there's not much more to be improved. Yeah. So you can just become cheaper. You can bring a little bit more mass into orbit if your whole rocket becomes lighter, these kind of things. But if once this is going into kind of mass manufacturing, so if they really make something like 1,000 starships, what they plan to do, so then that's solved. Yeah, it's you can hardly do better than that. Yeah, so the Chinese are doing it right now. Yeah, so. Let's say if in Europe, I'm not so sure or convinced if this is also going to be followed. But then you have, probably also Jeff Bezos with Blue Origin will get in the area. It's great. Competition is always good, but the access to space, just look how the numbers were falling down. When I was going to ISU, so we were counting with $20,000 to $25,000 per kilogram that you put into orbit. Now with Falcon Heavy, whatever, if you're lucky, you pay $2,000 per kilogram. And if they do this well with Starship, well, it's $100 per kilogram. This is like what I pay with UPS if I want to have a package, going from Germany to the UK or whatever, and put some insurance on top of it. So it's the same price. So that has been sold. A couple of years, access to space is affordable enough to just take it for granted. This is just a way of transportation that everyone is free to use.
Yeah, yeah, you brought up an excellent point, and I wanna poke on that a little bit. That would you agree that in the basis of where we are with SpaceX, Blue Origin, relativity space, ways of manufacturing in the launch industry, to improve from Earth to orbit, it's become an engineering problem?
Yeah, for sure. There's no physics factor that stops you from doing so. Yeah, it's
And Elon, I want to talk about that a little bit because it seems like he's become a very good prominent figure not only in the space industry but also, he revolutionized the automotive industry from Tesla and with Tesla, and he's betting on making the space industry a primary. And is he going in the right direction? The concept that or the bet that you would put on Elon today to make the industry better, would that be appropriate? Or would you bet on Elon to make the space launch industry better?
definitely. Yes, absolutely. I'm a huge fan. I was fearing actually. So before Elon actually came to stage, so my fear was that until I retire, I'm not going to see any human mission to Mars. so this has always been postponed, and it's a huge international effort, and maybe in the mid-30s, maybe mid-40s, yeah, and who knows, and this is really a top priority or not, yeah. Maybe we stick with robotic probes. It really needs someone to decide, oh, well, we're going to do this, and this person is not limited to political terms. So not that in 4 years we're changing because something else came up, which is also important. And so Elon Musk apparently is also an excellent scientist and engineer. So he understands exactly what needs to be done, and he can manage a big team. Plus he has the resources necessary to do so. So that's what I said. This is the chance of a century. Yeah. So it's like Tesla and Edison, invented and revolutionized how we deal with electricity. So Elon Musk is revolutionizing transportation. Yeah, like Henry Ford revolutionized how to build an automobile. Now it's the next revolution.
Yeah, and you brought up a really good point there, and I'm hoping to expand on this a little bit here for our listeners, is that a lot of great names have done a lot of good things because they were able to do it by themselves or with a great team or able to manage a great team. But with Elon, it's very, very interesting that he did something on the basis of other principles, and he was able to improve on that by creating multiple roads of efficiency. But do you think that he'll be able to figure out a way to do the next big thing after the rocket? And what do you think that next big thing after the rocket could be?
Um, well, I think he will be very, very happy if he gets a Starship really up and running, and for him the next big thing is to build a city on Mars. Um, that's a huge challenge. It's not, oh well, we cannot go to Mars. That's great. There are many things that need to be done. We have to produce propellant there on site. This city must be self-sustained. Yeah, you have to produce food. You have to do this. Well, you have to cope with radiation damages and whatever for people. There are many things that need to be done, especially on the engineering side, to have a self-sustaining city on Mars. So transportation is the first step, but there are many steps to follow. So I guess he will go towards that. So the technology is necessary to have something completely self-sustained. And actually, you can use that type of technologies then to build a generation starship, to go somewhere else.
And that brings up a really good point also, because I'm very curious to learn and hear about what your thoughts are on where Starship and the next versions of Starship per se, and what kind of innovations will they involve, and what kind of new principles evolved from fundamentals they will involve. And brings up a good point which you're really interested in, and I've read some things about this idea of breakthrough physics, which goes beyond the Earth's orbit, and for us to be able to travel as a species to other planetary bodies. What are your thoughts there? What would be best for us to do from Earth orbit to the moon and to Mars and to further on interstellar?
Okay, again, those are the two things. So we can, with Starship, we can go to the moon in 3 days. And if the ticket is, the price of a business class ticket from Europe to the US, then that's fine with me. You don't need breakthrough propulsion to do that. That's great. Yeah. So Moon, Mars, and maybe again half a year to Jupiter. We will do that. Yeah. Fortunately, with Elon Musk and SpaceX and whatever, we will do this. It's just a matter of time, and not, well, in the next decade, we will have this Mars thing going. Maybe we will start and already maybe exploring maybe towards Jupiter, whatever, because the moons there are really well, they're very interesting. There could be life there. It mustn't only be Mars. Um, yeah, and terraforming, whatever you do, that's maybe the next thing here. Well, the go interstellar, this is again something else. And maybe let me give you an example of what kind of a challenge that is, and some standard solutions and the non-standard solutions. So let's imagine you would like to go interstellar with a spacecraft the size of the space shuttle, okay? Because this is actually, the space shuttle is actually quite big. It seems small, but it's actually quite big. And let's say you want to take the space shuttle and just go to the next star, so Proxima Centauri. We know there's maybe an interesting planet. They recently found a signal that may come from there. Maybe we can check out, who is behind that signal. Breakthrough Listen did that. And so I just want to go there, let's say in 40 years, because 40 years, the time span, uh, I could still be alive, maybe to see, what's going on. And the space shuttle is big enough that I can take some canned food with me for 40 years, plus some spare oxygen to still be alive, and a couple of books and whatever to make that trip. All right, so space shuttle would work for such a 40-year-long trip. The thing is, what kind of propulsion system could bring me there? Well, let's take the best propulsion system that is around that I can take off the shelf. And the best propulsion system there is a nuclear bomb. Okay, so this is the best. So this is EMC square. Cannot do better than that. Direct conversion of mass into energy is the best. And I just take a bomb, I put it behind my spacecraft, I push the button, it ignites a huge explosion, much better than everything they're doing with chemical propulsion, and off I go, okay? I can design my spacecraft in such a way that this push and absorber plate, yeah, is good enough that it withstands a couple of thousand nuclear blasts. So that can bring me to a really significant type of speed. So that's the best thing you can imagine. That has been done. Yeah, so I mean, the concept was developed called Project Orion, 1950s and 60s, and but when they saw that the Saturn V rocket was doing fine, well, this project was stopped. But this is something that, nuclear bombs. This is actually a mass product that you can take from these intercontinental missiles, and you can do some much better use with that. Just drop it behind your spacecraft and off you go. It's the best that we just came up with. And the thing is, now I take nuclear pulse propulsion, so nuclear bomb, the best there is, the space shuttle, in 40 years, Do you know the mass of nuclear bombs that you have to carry with you to do that job? It's the mass of the sun. Okay? And that's just to the next star. So that means forget it. Okay, so it's not going to happen. Not with that
That's
type
not
of
gonna happen.
technology. So there are
Yeah,
now two options. Option
correct,
A,
correct.
okay, it's not possible. It's not what's not possible. Well, it's not possible in 40 years. It's maybe possible in 10,000 years. Okay, then I need a generation starship, some huge that has all the infrastructure for a whole civilization, to live. But 10,000 years, it's a long time. It's from the Stone Age, up to modern times, and all of that in a confined space, totally crazy. Yeah. So that's one option that maybe you can do that, but very unlikely. And I think there's a much better option B, actually, and maybe this was our fate, as I think for humans. It's actually going to be a computer that we will send on this journey. The computer maybe is not as bored as we are, for 10,000 years to, think what we can do. Maybe it was our destiny, for humans to develop artificial intelligence, and to have a being that we develop a being which is not limited by our biological processes, and to develop something. So you can think about this in 100 years for sure. We have something. I mean, they predict that by 2040 or whatever. So artificial intelligence will bypass human intelligence. Well, you add another few decades and you have something very solid and robust. And in 100 years or whatever, we will send a probe to all these different star systems. It will be like, yeah, I'm not saying the Borg in Star Trek or whatever, yeah, but artificial intelligence, which is not limited by this, it's just a time factor. It's just us humans. We want to do things quickly, but well, there's the speed of light limit and whatever. It takes a certain amount of time to go somewhere. And if it's just us which has the problems, then, well, it's the artificial intelligence that can do it, and they can explore the universe. So that would be option B. So either you have a generation starship, or you do the artificial intelligence option, unless you circumvent this problem of how we do propulsion nowadays with F is m times a. And as I told you, didn't finish that. If you have negative mass, yeah, there's a huge trick that you can do. So imagine that you have now positive and negative mass just next to each other. And let's say one is positively and the other one is negatively charged. So they attract each other. They attract each other, and the positive mass, is being attracted to the negative one, the negative attracted to the positive one. And the thing is that this negative mass means that this attraction direction for the negative mass flips. And instead of moving towards the positive mass, it's actually now going away. So this two mass system, this inertial dipole, positive and negative mass, will start to self-accelerate. Okay? So you don't do anything, you don't inject energy or mass, and this dipole is starting to self-accelerate. Yeah? It's an academic exercise to think if it will reach a speed of light, if it will even go beyond the speed of light. Yeah, this is something that we have to prove, like Chuck Yeager did with breaking the sound barrier. I would be happy already with going with the speed of light. That's okay for me. And so you just have to build something that has minus whatever kilogram. And the thing is that what Professor Zeilinger did with his crystal in the neutrons only get into this state inside this crystal. So that's the problem. We need negative mass here on the outside. It could be that there are negative mass particles in the universe. It's not forbidden. It can just be that we just haven't found it. We have to keep digging or look with space probes. Maybe it's related to dark energy, whatever. No one knows, yeah? So it can be that there is this kind of discovery being made. Hey, We just found particles that behave this has this weird behavior. I push on it and it comes to me. If you found that, job done. You develop a space drive. So then space is moving. You don't need to inject propellant or do something with this. Yeah. Um, Another method also that you can think about is to use the vacuum background. Yeah. So to use the vacuum background we sit on this huge energy density called the zero point energy, to use this somehow as a propellant. So this would also use our ambient space as a propellant. So either you build a space drive or a generation spacecraft or artificial intelligence. Those are the three things.
Or artificial intelligence. Yeah, I mean, it's. I'm glad that you brought up the and I was reading on the project that you're working on, the Space Drive project, and something very interesting that led me to understanding that, and actually getting a brief understanding of that, was your work on or the work on breakthrough physics, and to discover new approaches and in approaching this type of problem. But I'm also very curious about the work that you did on gravitational fields in regards to electrical propulsion systems, and that which received quite a bit of international recognition. Can you give us a background on an insight onto that discovery? How did you end up there?
Well, how I came into electric propulsion, when I studied physics at the Vienna University of Technologies, this was at a time when there was no internet. So my children, they cannot believe how it's possible to live in a world without internet. And so there actually it was a booklet with all the lectures in there, and you could go through the books. Through the book and for all the lectures, and to see what's being offered and what you can do. And so I was very interested, of course, in space propulsion. I was very keen on physics, and yeah, I had my little lab in my children room, and I was building huge high voltage power supplies and this kind of stuff, because I thought I'm going to need that. And so when I was browsing this book, I saw one lecture called Electric Space Propulsion. I said, aha, that sounds more or less exactly like what I would like to do. And I was in the second semester, so very early on. This was a course for graduate students. I immediately registered. I said, well, it's exactly my topic. And that's when I was first exposed to what's being done in so-called electric propulsion. So in electric propulsion, it's not like, in chemical propulsion, you combine two propellants to create a hot gas, which is doing propulsion. Electric propulsion, you actually using electric and or magnetic fields to create acceleration. And so if your propellant is charged, so you have ions, plasma, you can accelerate that with electric and magnetic fields to much higher speeds compared to chemical propulsion. And that means that your propellant efficiency is much higher. You need much less propellant to do the same job. So that's very interesting. The downside here is that you have to bring your own electric energy with you. And so you're limited, let's say, by the power that you get from solar rays. That improved over time significantly. So when I looked into this in the early 1990s, this was still called advanced propulsion, and that's going to come or whatever. Now electric propulsion is a mainstream technology. You have kilowatts, tens of kilowatts available in a spacecraft. There's lots of power available to electric propulsion, and that's the so-called number one choice for in-space propulsion. So once your satellite is in orbit, you use electric thrusters to keep there, change your orbit, change orientation, whatever. Starlink satellites from SpaceX, they also use their own electric propulsion Hall thruster on board to do the job. So electric propulsion it's let's say the better propulsion option, but you're limited to the fact that usually you need a good vacuum to operate this type of thrusters. So that means you can only do this in space. And another limit is that the amount of forces that you have are much lower because you're limited by the energy. Just think about, if you think about the power density of a chemical combustion chamber, Yeah, so that's about 1 gigawatt per cubic meters. A gigawatt, that's the power output from a nuclear power plant. So 1 gigawatt on the size of 1 cubic meter. Yeah. On a satellite, I don't have gigawatts available. I usually have kilowatts, and that means I have much lower thrust. But who cares? It just, it takes maybe a few months to get into your orbit. So what? So just takes a few months, but I just use a fraction of the propellant, and then my spacecraft can become much smaller. It's much cheaper, and so on and so forth. So electric propulsion, it's a big thing, and yeah, I got my hands dirty with lots of electric propulsion options. So one that use liquid metal, especially for propellants. So we developed a very precise so-called field emission thrusters, and I'm building very classical electric propulsion thrusters already with a always with a certain spin. I always see myself at least 2 steps ahead of everyone else. So if you want to do innovation, I mean, I don't want to do just what everyone else is doing. So I always come in with something very unusual, and that's good. So that's why I'm in university. I'm really trying to push the boundaries and do something new. So I come up with new materials, new manufacturing schemes, new layouts and whatever. And yeah, we have lots of fun building all kinds of different thrusters and improving them.
It's very. I'm glad that you brought up the idea, the fact that you where you are doing this. In terms of the environment that you're doing this in. It's a very collegial environment, very involving environment where a lot of freedom can take place in terms of research. And I'm very curious to understand that over the course of time, and I'm sure the audience also is that what are some of the promising concepts other than the ones that we've already talked about? We've talked about nuclear, we've talked about Hall thrusters, we've talked about various types of electrical propulsion systems. What are some of the promising concepts that you think that in the next 20, 30 years will be more prominent than others?
Okay, it's always very hard to predict the future, right? If I would knew what's going to happen in 20 years, then well, I can just give you some educated guesses. Um, let's say for electric propulsion, the thing is that it became such a major business. The key thing here is how to really drastically cut costs. So I cannot tell you what's going to happen in 20 or 30 years or so, but I can tell you in the next 10 years, lots of things are going to happen with additive manufacturing, new materials, smarter way of doing things that, thrusters that cost millions will sell for a couple of 10,000s or so. Yeah? So that's going to happen. Yeah. So that's already happened. Again, SpaceX, what is launching with Starlink? 15,000 satellites, 15,000 Hall thrusters. You just have to compare this to just a few years ago. When people tried to make a business case for electric propulsion, and they said, yeah, let's assume they're going to launch maybe, five big satellites in the next year or so, and we get a market share of 20%. So we can sell maybe a couple of thrusters or so, okay? And now someone says, oh, I'm going to build 15,000 satellites. You cannot sell your million euro dollar type thruster anymore. It's just not going to be possible. So the thrusters that we have are pretty good. So you just drastically improve in cost. It's just going to be much, much more cheaper and more accessible to everyone. Yeah, so that's a big driving factor. Yeah, of course, I'm always working on some also unusual electric thrusters concepts, and well, just read my publications. I'm not going to tell you what I'm doing right now, but it's
Yeah,
fun.
yeah,
It's
absolutely. And
fun.
we'll let our audience have a look
Sure,
at. Yeah,
sure.
we'll let our audience look at a few papers that you have put out there. But I'm curious to hear your thoughts about the large governmental and non-governmental and commercial organizations that are sort of like conducting other types of research, which I'm sure that you have an idea. NASA, Google X, Starshot, uh, conducting research into light sails and warp drives. Do you think that we're at a point where it is close to an engineering concept or an engineering problem, whereas, or it's still a physics problem?
Again, to make it quick for the warp drive, again, there's no one knows what to do to build a warp drive. Yeah? Other than that, I just told you, go and find -1 kilogram, and job is done. So I'm trying to fool around the best that I can to find an answer to that problem. I'm testing everything there is. I'm trying to develop the best test infrastructure to find such kind of effects. So I'm concentrating on building really the best thrust balances and whatever there is, and then to put everything onto the test, and not only test other concepts, but also come up with interesting experiments to try to look into corners that have not been assessed so far. So you always find something new or unexpected if you look with a new method, or if you look into a regime that no one has ever checked before. So that's what I'm trying to do there. But I mean, I cannot give you any kind of guarantee, because no one knows if we're going to find something. I really take this as it's just a trick. It's just, once you know how to do it, it's just a trick, and we could have done this already. But Jules Verne once said, everything that we can imagine must be possible because we're part of nature, and so it's just a trick. Okay, if you look, Arthur C. Clarke said that any sufficiently advanced technology is indistinguishable from magic. If 100 years ago I would have showed someone a smartphone, the best magic trick ever, cannot figure it out, right? So I just keep going. I keep going. I try to dig. I try to find. I build better test equipment, whatever. I don't stop until I find this magic trick. Okay, but there's no guarantee here. For these other propellant options that you just said, like solar sails and whatever, for sure that's going to come. That's great. Propellantless propulsion. This is well, again, it's not something new, because it has been flown. It's just being improved and being improved on. But we have new materials. We have maybe in space manufacturing possibilities, bringing 3D printers into space, which can build huge solar sails. And we just use photon pressure. So the sun does not only provide us, light, but it also has a momentum associated with it, and that's fantastic. We can sail around the solar system, and well, Breakthrough Starshot wants to go if interstellar with that, but there are a couple of challenging technologies that need to be solved to do so, which is of course also, it's great. They also keep going, and who knows where they will end up with. But it's great that you start up with something. If you don't start, then you will never achieve anything. So if I say, oh, the warp drive, forget it. Yeah, show me one concept in physics that tells me that it's going to work. I can't. So shall that means I shall not give it a try? I don't think so. Yeah, and this was throughout history. Okay, it happened so many times that you discover something totally unexpected. Yeah, and superconductivity or whatever. No one ever thought about this. Yeah, so it can happen. And what did Kamerlingh Onnes do? He tried to test in a regime that has never been tested before. So what's going to happen if I measure electric resistance at very low temperatures? No? Well, he found out that at a certain critical temperature, he disappears. So I'm also trying to look into regimes no one has looked before, or with a resolution, with a precision no one has done before. I'm trying to do that, yeah, and I'm trying to find something unexpected.
And this is and this brings up an interesting point that I'm sure that you have some thoughts on. The lack of applied research power or abilities of the past. The freedom of research connected to doing cutting edge type of research and the continuity of that. There are a lot of organizations, DLR, Flatiron Institute, Simon's Foundations, that are making tremendous progress and pretty steady as they're doing it. Do you think that in terms of the power and the capacity that we can apply to research and development is decreased over time, can we do more in terms of continuing to provide the researchers for the future more resources?
Well, of course, it's very essential to have a very good research environment. So again, I'm very, very fortunate that I was always, working in very good organizations that provide this type of freedom. And especially if you want to do something, that goes far into the future, well, the best environment there is university. So this is, we think about the future. We're trying to be extremely innovative. So that's the right place to do this kind of research. And also at DLR, whatever they told me, the worst thing that can happen is that we learn something from it. So it's the perfect education project, I can tell you. So my students, if we find a warp drive or not, yeah, but whatever we do to solve very challenging measurement problems, yeah, or look into things no one has ever looked before, they have a fantastic education, yeah. So this is much better than to repeat when everyone else is doing everything. So this is a great thing. And of course, we can always do more. And something that I encountered, which is something very important, is to drastically reduce bureaucracy. Because also many people ask me, how come SpaceX can, launch people into space and NASA can't do it? I said, well, I think I know exactly why. Um, when I was a PhD student, I was very fortunate to spend a few months at NASA JPL, and it was really a fantastic time. And I remember, so I got a desk, and I wanted to just get some ballpoint pens and whatever. And I went to the secretary and said, well, I would need a couple of ballpoint pens. And she asked me, what's your charging number for that? Said for a few ballpoint pens. Okay. Oh my God, we will never ever go back to the moon. So I knew it's going to be impossible. Okay, we cannot do it. Someone at Boeing told me, if you're going to order as a private individual, if you're going to order the space station, it's going to be for a 1/20th of the cost than if NASA and all those international partners are going to order it. So it's absolutely ridiculous. Are you kidding me? Yeah. So that has to stop immediately. So can you imagine, you cut loose the amount of money and the amount of time that researchers have now to put into being productive instead of doing meetings and filling out these forms and bureaucracy? This is ridiculous. So that's it.
and 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 community plays a large part in helping move the government and organizations in that spectrum. And I think, from a researcher perspective, I'm curious to hear your thoughts on, from a research standpoint, not the administration of the university or the bureaucracy of a specific government. you know the involvement of the crowd slash public into helping research become more and more involved with the citizens. And how can we do that? The idea that current researchers are often have a micro community of PhD students, master students who are conducting these specific type of research. What can we do to enhance that citizen edge research? Do you have any thoughts on that? The SETI Institute involved a very first community where they inspired research initiatives through crowdsourcing.
Um, okay. So yes, if of course if private individuals come together and say, well, we would like to fund the warp drive and whatever, it's fantastic. So I can open an account where I can accept this kind of donations. So if that's possible, of course that's fantastic. Yeah, if private people are deciding that this is important, and things can move into this direction, that's for sure part of the game. And yeah, we can see this probably also more frequently, maybe also because people are trying to see, if they look for a good investment. Yeah, maybe they want to invest directly into an idea instead of buying shares or whatever. I mean, you don't get any interest at the bank anymore, so yeah, you have to invest. So that's for sure something that's going to come. And also there, I can just encourage to say no strings attached. Okay, I give you some money. Okay, and yeah, I trust that your ideas will work out. But the best environment for you is to have the least strings attached for a researcher. The best it is. Yeah. So if you look, for example, at Bell Labs, also the stories, Bell Labs, they get the best people, and they say, well, you can do whatever you like. Yeah, and your partner gets a nice job too. Tell us what you need, and just do whatever you like to. Um, I was told by another famous professor. He became professor at MIT. He said when he became professor at MIT, the president from MIT came to him and said, I don't care what you're doing. I really don't care. Okay, you can do whatever you like to. In 4 years, I'm coming back, and whatever you did must be world class. That's the only thing that counts. Okay, whatever you do, you must be very good, but don't constrain people. Also, for example, when I'm trying to hire faculty or something like this. So right now it's being done in a very narrow thing. Oh, we need an expert in exactly that and that regime. It's very hard to find this type of people. I tried to convince our faculty to go a little bit, other direction, to saying, well, let's say we need someone excellent in aerospace. I don't care particular what he's doing. It must be just a great fit. And so to keep open, don't put strings on people. Just let them do. And it can be that today he's doing that, and maybe in a year he becomes, an idea, talking to a colleague or whatever, doing something completely different, becomes really excellent in that. So don't, put strings on people. Let them go. Okay, let them go. And that is your path to innovation.
Freedom.
Yeah, freedom, and and no bureaucracy. Okay, so
Freedom and no
this
bureaucracy.
is
Yeah, excellent.
this is that's a sweet spot.
I know I'm very cognizant of time, and I have a few questions for you about economics of space, and we have dived into it a little bit, but I'd like to get your thoughts on it before we wrap up our episode here with you. I am very curious, and I'm a very big proponent of sustainability, and ensuring that we do as less moving forward in mitigation of the climate change, and ensuring that we don't get to that point of no return. How can we make sure that we do that to the launch market and into the orbit?
To have a fully reusable spacecraft is your first step, I think. I mean, right now, you launch something and a huge chunk of useless mass is floating around space. That's ridiculous, right? So it's already a very good option to go into space and come back and don't leave anything behind. I mean, that's the best there is. Um, of course, if you put 15,000 satellites into space, yeah, we will not go back to the days before Sputnik, where the sky was completely empty. Um, yeah, I think it's kind of part of being humans. we grow, we develop, we go somewhere to stay. Of course, this has an influence on nature. That's undeniable. Especially, if you do it too much, yeah, it's very hard. You cannot say to people, "Hey, we are now 8-9 billion people. Stop." How do you want to go to someone and say, "Hey, I think you should not have a child"? It's not right. It's not really possible. It's part of being human, that these things develop. Nature, on the other hand, reacts, as we can see, and that will put limits to everything. So nature will react drastically, and we try to put things together. But just the fact that we are so many people, let's say everyone is going to use an electric car. That's great. Now where's all the power coming from? Yeah, and so on and so forth. So if we do too much, there is always going to be a problem. Always, no matter what you do. And yeah, we have to live with this.
But do you? So here's a question for you. And this is coming from a very economical and regulatory standpoint. The rules that FCC brought forward in terms of deorbiting capabilities on board satellites, which increases eventual demand for electric propulsion systems to be on there on board satellites. Do you think that the this will help the orbit become decluttered, or do you think that this is going to be one of those scenarios where I have this capability, but I want to make my satellite stay up there for longer?
Mhm. Well, for example, here in Germany, it's already, the regulation that if you bring something into space, this something has to deorbit in 25 years. Yeah? So either you have to deorbiting means that you really get away from space, you re-enter again, or you move farther away such that you make space for someone else, for example, going to the geostationary orbit. But that means that you just move your graveyard a little bit away. You still put huge chunk of stuff up there. So again, Elon Musk is doing this very smart with Starlink. The Starlink satellites are flying in such a low orbit that even if you don't do anything, they will deorbit automatically in a year or so. So you don't keep, if you launch as many satellites, you don't keep them in space. That's something great already. But again, it's yeah, we will have. I mean, electric propulsion, whatever. You can you have deorbiting strategies are very important. We're also working on a great deorbiting project. But yeah, maybe once we have a fully reusable spacecraft, we can really deploy, I don't know, huge nets in space to really collect all the garbage and bring it back or whatever. But yeah, it's not moving into the direction that actually the sky is becoming cleaner. It's actually going in the other direction. There will be more junk up there for sure. Just imagine, one satellite hits another one. That creates so much more junk. Yeah, we screwed it up, unfortunately. There is
Absolutely.
yeah.
Absolutely. I totally agree with that. And I think hopefully we don't get to a point where it becomes a point of no return for us before we get to that climate change point of no return. But like I said, I'm very cognizant of time, and I don't want to take too much of yours. I'm very curious to hear your thought on this. To each and every single guest, we typically ask, how do you think that we can help ensure that space continues to move forward?
um how can we ensure that space is moving forward? So I think this is again something very natural. Yeah. So we came from the water. Yeah. We came onto the land. We built ships to go to other continents. Then we discovered how to fly, and the next thing is space. This is in our DNA. Cannot stop this. So even if you would put a stop on all space activities, just wait one generation or whatever, new politicians, and this will come up again. It's part of our DNA. So it's going to happen. The best support at the moment, if you really want to go, further with space, is to support Elon Musk and maybe Jeff Bezos or whatever. That's the best I can think of. This is again the chance of a century. It would not happen otherwise. So it's the best I can do.
Well, I think Martin, I'd like to add on to that point to support Martin in helping ensure that his research continues to move forward. But I truly appreciate the time that you've taken today, and I'm sure our audience has as well. And thank you so much for coming and dropping by. I am sure that eventual in the future, with the amount of work that you're doing, we're going to have you on board again for another topic similar to this, or even further on, because I'm a big fan of the work that you've done.
Thank you so much.
And I think it's going to help evolve
Yes.
and improve the industry as a whole. So thank you so much.
Thank you very much. Very kind.
Well, folks, thank you for joining us on another episode of Space Forward. Stay tuned for more deep dives and explorations, journeys we have in store for you. Follow us on Spotify, subscribe on Apple Podcasts or YouTube. See you next time.